Okay, so I think what I'm going to do is go ahead and get started. And if people join a few minutes late, they'll only miss the boring stuff that I say. So they'll probably get the meat of it. So welcome everybody to Compelling Conversations. This is an activity we do, once a month or so, where we bring in some of our amazing researchers and sometimes alumni from UCI and talk about interesting topics. And today, I'm really excited to talk about the next quantum revolution. You may have heard a bit about quantum computing or even quantum devices. There's a lot of hype in the media, but there's definitely a kernel of truth and sort of the excitement that I think people feel about this area. And we have a lot going on at UCI in this area. So very excited to kind of open it up. Just so you know, if you'd like to text to give to support any of the research or these kind of activities that we do here in physical sciences, please feel free to do that. You can text the numbers, text the letters PSCC to the number 41444. And any kind of donation, even at the sort of $5 level, actually can have an impact for the kind of things we're trying to do here. So thanks very much. During the discussion, we're going to have a very informal conversation. And if you have questions that come to mind while you're listening to us, please just go ahead and jump on the Q&A there and type it in, and we'll try to incorporate that into this conversation. So with that, let me give a quick introduction to everyone. First of all, let me start with Bill Evans. So Bill is a distinguished professor of chemistry at UCI, and he's the director of the newly established Entanglement Quantum Institute that I think he'll tell us a bit about. Professor Evans's research focuses on inorganic chemistry and specifically rare earth elements. He's got more than 500 publications, and with that, he's certainly among the most accomplished faculty at UCI, and so we're really pleased to have him. He got his undergraduate degree in chemistry from the University of Wisconsin, his PhD in chemistry from UCLA, and before coming to UCI, he was a postdoctoral fellow at Cornell. Next, we have Sandy Irani. Sandy is a professor, a full professor in the computer science department at UCI. She's also the vice chair of the computing division in the Donald Bren School of Information and Computer Science. Professor Irani is interested in the design and analysis of algorithms, and in the last few years, she's been working on quantum computation and quantum information science. She holds her undergraduate degree in electrical engineering and computer science from Princeton, a PhD in computer science from Berkeley. She did postdocs at Princeton and UCSD before coming to UCI. Finally, Javier Sanchez Yamagishi is an assistant professor in the Department of Physics and Astronomy. His areas of interest include electronic phenomena and 2D quantum materials, graphene, quantum sensors, and nanofabrication. He got his undergraduate degree in physics from Rutgers University, a PhD in physics from MIT, and before coming to UCI, he was a postdoctoral fellow at the Harvard Quantum Optics Center. So with that, I'm now going to go around and have everyone say a few words just as a words of introduction. And so let me start off with you, Bill. Can you tell us a little bit about how you came to be working on these interesting questions related to quantum science and a little bit about your trajectory here?
Sure. Glad to tell you about that. So I'm an inorganic chemist. I'm a synthetic inorganic chemist. I like to make molecules. And it turns out I like to make molecules with these elements called the rare earth elements. I'll see if I just put this up here. This is a little rare earth element game that we developed at UCI. So if you have a 6-year-old and you want them to learn samarium, terbium, europium, lutetium, this is the way to go, okay? So these rare earth elements, I'm gonna try one more visual here. These rare earth elements are the ones at the bottom of the periodic table. Not getting it quite there. There's a bit, the bottom of the periodic table where my finger's pointing here, that you never studied very much in school. And these are unusual, and I got interested in making molecules with them because they were rare. Also because they have unique properties. So they're called rare earth elements, but they're in our lives all over the place. They're in the computer giving you your red from europium and the green in the background here from terbium. They're in your catalytic converter. MRI imaging uses gadolinium. Catalytic converter uses cerium. The best magnets in the world are iron neodymium boron magnets. Anyway, I'm I'm a synthetic chemist. I like to make molecules for fun. I just to create new knowledge. And some of these molecules have very, very interesting properties. That's why we do it. Some of them are catalysts. Some of them have interesting physical properties. So we made some molecules that were single molecule magnets. It's the smallest magnet you could imagine. It's the size of a molecule. And we also made some molecules that were qubits. And I didn't know what a qubit was when I made this molecule, but I collaborated with a group in Manchester, and they did some measurements on our new molecules and said, this is a qubit. So I had to look it up and find out what a qubit was. So I've come into quantum science from a very strange way as a synthetic inorganic chemist, but it's a very interdisciplinary area. And so there's a lot of people that are contributing. So I think the other people will tell you more about quantum science than I will, but that's how I got involved.
Thanks so much, Bill. Well, speaking of qubits, why don't I move on to Sandy then? Sandy, tell us a little bit about what you work on and your interests here at UCI.
Okay, well, computer scientists started getting in the game of quantum computing, I guess, in the early 90s. And there was a famous lecture by Richard Feynman in which he noted that simulating quantum systems was getting to be beyond what regular classical computers can do. So he suggested, well, if you want to simulate quantum systems, maybe your computer should use the properties of quantum mechanics to compute. So storing information at the atomic level and harness the unusual properties of quantum mechanics to compute. And since then, computer scientists have been wondering, well, if you could build one of these quantum computers, what could you do with it? So I got in the game relatively recently in the last 10 years. And so we're looking at different things. One is that, given an idealized quantum computer with 1 million fault-tolerant qubits, what can we compute with this? And it turns out that quantum algorithm design is very, very different from designing algorithms for regular computers, a different toolbox. And so we don't really have a good grasp yet on what they could do, even the dream scenario of building them at full scale. And at the same time, now there have been some incredibly exciting developments in industry with Google and Microsoft and IBM getting in the game and producing these, what we call NISQ computers, near-term intermediate scale quantum computers. And the qubits tend to be noisy, but we've got qubits in the tens, 50 to 100 range. And so we're also asking at the same time, what can you do with 50 noisy qubits? And that seems to still be beyond what we can simulate with a classical computer. So how do we harness the current generation to do things that are useful and beyond what we can do classically? So
great. So I can't wait to ask you a few more questions. Before we do that, let's bring in Javier. So Javier, talk to us a little bit about what you do, how you got to UCI, and then pretty soon I'm going to ask someone to explain what a qubit is.
Yeah, sure, no problem. So I got interested so I'm an experimental condensed matter physicist. I have a lab here at UC Irvine that just started up a little less than 3 years ago. But kind of the way I started on this pathway was I started at Rutgers, the State University of New Jersey. And it was after a time when a lot of initial excitement around quantum computers had been built up steadily over the course of the 90s and into the early 2000s. So I was really into the idea of quantum computers, idea of qubits, and so I went on to go to grad school, and it seemed like all the initial cool stuff had been done. And at the same time, there was this new class of materials that had been discovered, which are known as two-dimensional materials. So these are materials that can be just a few atoms thick or even 1 atom thick. In the case of graphene, which is a hexagonal lattice of carbon atoms. And it turned out they have really cool quantum electronic properties. So I got really into studying and trying to do some interesting experiments on these materials. But there was always this idea in the back of my mind that this could be potentially useful for quantum devices, which will hopefully explain a bit more what that means later on. But basically devices that take advantage of quantum mechanics. So that was a lot of fun. That was my PhD. And but then after that, in the end, I'm studying these materials, right? But when you study kind of cutting edge new materials, you're always interested in new ways of measuring them. And so when I went to go for my postdoc, I thought, okay, I want to learn a new technique for measurement. And that's how I ended up at the Harvard Quantum Optics Center. I also wanted to change kind of what I was doing. And what was exciting at the time there was that they had figured out that this type of qubit, which is known as a nitrogen vacancy center in diamond. It's a defect in diamond, like you would have on a diamond ring. It turns out it's a very good qubit. It's a really great room temperature qubit, and it's actually a really good sensor. And so that was what I worked on my postdoc, applying this quantum sensor to measuring materials, which I was interested in. Fast forward to today, so now I'm starting up this lab at UC Irvine, as I mentioned, and I'm really trying to explore this space of new materials, which we call quantum materials, that take advantage of quantum mechanics, and using those to make new types of quantum devices or quantum sensors, which also we're hoping that we can use to study the materials that we're interested in, discovering new types of materials. So that's kind of my introduction of my deal.
Wonderful. Okay, so I think now is the time. We use this word quantum science in the title of this thing, and we've been talking about the word qubit. Who wants to take a crack at defining? Maybe let's start with quantum science. Bill, do you want to take a crack at defining quantum science? I'm going to throw you under the bus here and ask you a real tough one.
No, I'm glad to do that because so I need to tell a little bit about the Edelman Quantum Institute. So
please do. That's a great time to talk about that. Thanks, Bill.
A man named Roy Edelman came to see me one day and was interested in supporting rare earth science, and my jaw just dropped because of all the places in the periodic table he was interested in rare earth science. He's also interested in quantum science, and to make a long story short, he's supporting that effort with forming an institute at UCI, the Edelman Quantum Institute, and it brings together rare earth chemists like myself and quantum scientists, more quantum scientists like Javier and Sandy, to interact. These are groups that would normally never talk to each other because we just travel in different scientific circles, and try to come up with something more than you would get just by working in your own little circle of area. So there are now 19 faculty members in the Edelman Quantum Institute at UCI, and this is the prelude to your question. I asked them what quantum science was, and they got into a big argument because everybody had a different idea of what quantum science was. And some people thought it was more what Sandy does, and some people said, wait a minute, it has materials, and I'm thinking it's got chemistry. And so there's your answer. Quantum science is a broad activity that involves everything from math and computer science to molecular chemistry through condensed matter physics.
Yeah.
And you know, people say, I guess if you look closely enough at anything, it's quantum mechanical, but you have to look very closely, like Javier is able to do with his instruments.
So yeah, let's build off of that. So
I disagree with that definition.
Yeah, that's great. That's what we want. The audience
cause some controversy.
But let's build off of that. So one thing you talked about, Javier, was quantum materials, and you talked about using a qubit as a sensor. So what does it mean for something to utilize quantum, for something to sort of get in the nitty gritty of being exhibit properties that rely on, fundamentally really quantum mechanics, as opposed to, of course, my sport coat here is made of atoms and therefore quantum mechanics governs its structure. What's the difference between that and what we would talk about as a true quantum material? I know it's fuzzy, but what do you think?
Yeah, it is kind of fuzzy, and a lot of it has to do with just differentiating like conventional from unconventional. So what's happening here is just that, we just today, compared to say 100 years ago when quantum mechanics was being figured out, we just have a much deeper understanding of the implications of quantum mechanics. So I would say that quantum sciences is really about how, fully realizing that understanding, engineer and taking advantage of it. So can we engineer systems, quantum systems, which fully take advantage of quantum mechanics and basically realize something that's not actually found normally in nature? Okay, so there are metals out there. There are normal magnets that you put in your refrigerator, and those are, of course, based on quantum mechanics. And actually, magnetism is an extremely quantum mechanical phenomena. But those occur naturally in nature, right? Those materials. And so the question is, and we've uncovered their properties. So the question is, can we, with our modern understanding of quantum mechanics, discover something truly new that that we weren't able to observe before? So for example, about 15 years ago, an entire new class of materials was discovered called topological materials. And it turns out a lot of materials are this type. They're a new type of material class that we never knew existed before, and that came from our modern understanding of quantum mechanics. The flip side, the second part of that, which is not just understanding and taking advantage of it, but is also about control. Can we control quantum systems and engineer them to do what we want them to do? Can we make, so for example, can we make better sensors? Can we make better electronics? Can we make better computers by taking advantage of our control of quantum systems? So that's kind of my
great. And so now I'm going to ask Sandy. I know you teach a class for, I think it's undergrads, right?
Yeah,
on quantum computing. So when you talk to these undergrads about, first of all, you have to introduce what a qubit is. Right. Talk us through that. Pretend like let's just pretend I'm a dumb astronomer. I'm not, but let's just pretend.
Okay, so let's start with a bit, because we all have a pretty good understanding of what a single bit is. So your computer is storing information in ones and zeros, and we in computer science love to abstract things away, so we don't worry too much about whether the ones and zeros are represented by in a transistor or silicon or a vacuum tube. To us, it's just a 1 or a 0. A qubit, on the other hand, and one of the basic principles of quantum mechanics is that matter can be simultaneously in different states at the same time. So a qubit is partially in the 0 state and partially in the 1 state. And the extent to which it's in one state or the other is represented by a complex number. And it's just kind of mind-blowing that complex numbers sort of come in naturally. But when you think about, if you take a single qubit and now you extrapolate, let's say I had 100 qubits, okay? So now my system, there are 2 to the 100 different possible states my system can be in. So to actually represent a quantum state on 100 qubits requires 2 to the 100 complex numbers. So this is an incredibly rich source of information. It's storing a phenomenal amount of information. So you can see why simulators had trouble. You can't even hope to begin to explicitly store a quantum state of 100 qubits. But now what we in computer science are wondering is, well, does this allow us potentially to explore 2 to the 100 different possible solutions to an optimization problem simultaneously? Can we exploit this parallelism in some way to do something that we couldn't do normally on a regular classical computer? And of course, the rub comes in the measurement part. You can't just peek in and read off these complex numbers. You have to do some measurement. And when you do that, the state collapses and it changes the state. So you have to work with very carefully orchestrating, planning these different amplitudes so that when you measure, you get a meaningful response. So.
Fascinating. So my understanding is that, in an ideal world, you have this set of qubits, but in reality, the system might be noisy and you might lose that coherence. Javier, can you talk to us a little bit about that issue and why it's hard from sort of a hardware's point of view, which I think you're a bit more on the hardware side, Sandy's sort of software side?
Yeah, so just as background, right? So I'm an experimentalist, and I don't make quantum computers in my lab. I would say that I'm interested in the kind of individual qubit level, making that or applying them as sensors, right? But yeah, the core issue is that the reason why we don't go around and we're not just quantum objects ourselves is because all the individual atoms and electrons side of our body, they basically get in each other's way, and all the quantum coherence is washed away, and then you end up with just classical Newtonian physics. So the key thing is isolating all the different quantum objects from each other. So for example, you take an atom, which is a beautiful, wonderful quantum object. You have to take a single atom and separate it from all other atoms that would be around it, whether it be in a gas form or in a solid. So you have to take an atom, somehow isolate it. How do you do that, right? Like, how do you hold on to an atom? Turns out you use a laser, which is called an optical tweezer, to hold it in place. And then you have to pump out all the other atoms that are inside of a box. So you have to put it in a vacuum chamber. It has to be a very good vacuum chamber so that no other atom comes in and hits it. So you separate them all from each other, and then you also have to separate it from stray electric fields, magnetic field of the Earth. And if you do get rid of all those environmental influences, then you could end up with something that behaves like a quantum object for some amount of time. But that's just step one. Then, there's other steps, which is, okay, you can't make a computer out of one bit, quantum bit. So you now need to figure out how to start connecting them together again, but do that in a way that doesn't mess up, the individual quantumness of each object. And that's kind of the very tricky part.
I actually have a question for Javier.
Yep.
You mentioned quantum sensors a couple times. So what would I do with a quantum sensor? What am I sensing?
Yeah, so quantum sensor is based on this idea that one, quantum objects are very sensitive. That's why they're so hard to work with. Is right why there are no, it's not so easy to see quantum phenomena in everyday life, right? So once you've isolated all the environmental influences on a quantum object, then you can now selectively make it couple to something that you're interested in your environment. And this could be as simple as a magnetic field. So some of the best sensors of magnetic fields that we have are basically quantum sensors. Are based on quantum objects like atoms, are very good quantum sensors. Yeah, so it's as simple as that. It is the limit of a quantum sensor. If you want a sensor that is really, really tiny and really, really sensitive, then you're going to end up going to the quantum regime. You kind of have no choice. It's going to happen.
And the reason why, go ahead, Bill.
I would just join in and say, I think that as we go for quantum computing and quantum computers, the effort that we make to make new molecules and new materials is going to lead to new discoveries that we can't even imagine right now. And some of them may be in sensing, for example. So I'm quite excited about quantum computing and all of that, but I think there are other things that we're going to discover in the realm of quantum science in the next few years, 3 years, 5 years, that we can't even imagine right now, because we're pushing the limits of what the materials are doing, and we're trying to measure them in different ways. So yeah, I think there's probably even something beyond sensors that we can't even say what it is right now. That's exciting to me.
But in turn, one of the applications, the primary applications of quantum computers is going to be, hopefully, to design more quantum materials. So it'll it'll go full circle, hopefully, because that's one of the things that we believe that quantum computers will ultimately be very good at, is sort of plugging in parameters and figuring out how quantum materials behave before you can actually build them in the labs. So
yeah, and is it reasonable to think about the current way this is done as it's almost trial and error. You have some background experience, you build some material, and then you measure its properties. You say, gee whiz, that's interesting, let me try this. Is there some future where we envision actually designing ab initio materials using a quantum material that can enable sky's the limit kind of stuff? Is that kind of the hope? Is that one of the hopes?
Yes. I mean, that is a hope that's already being worked on now with classical computers, right? With the whole, say, data science revolution, right? And that's already, so before, I mean, even just in the beginning of my PhD, things were kind of at that level of like, do one experiment, do another, right? Trial and error. Now we're being aided by classical computers, but they cannot actually fully simulate the actual materials that we work with, because they're dictated by quantum mechanics. So you cannot use classical computers to fully simulate quantum mechanics. And I think Sandy, some of your research, right, deals with this idea of simulation of quantum systems, right?
Right. So that's one of the things we expect quantum computers to be very good at, is, certainly simulating the time dynamics. I start with some quantum system. It's governed by Schrödinger's equation. How does it evolve over time? People have really worked a lot on different quantum algorithms, quantum circuits to do that efficiently in different scenarios. So that's one of the primary areas of quantum algorithm design, is to do that.
Maybe it's worth talking about, like, what are we talking about in terms of new materials? What could these materials do that current materials can't do? Like, what's the dream?
Yeah, so it doesn't have to seem very esoteric or anything. We use this word quantum, but actually in reality, this really can just be new material, right? And the types of things that we think about are electronic and optical effects, right? So you want to make a better solar cell. You want to make a better transmission line for electricity. You want to make better classical computers even, right? Okay, classical computers are also running into the quantum limit, not even trying to. Sensors, as we already mentioned, and also
drug design, maybe.
Drug design, yeah, catalysis design, for example.
Superconductivity, room temperature superconductivity.
Yeah, that's a long running dream. It's a room temperature superconductor. A lot of efforts going towards that as well. So the idea with quantum materials is just that it could give us a type of material functionality that we can't even imagine right now. That's the thought by harnessing it. But it can also, a quantum computer, if we had one today, I mean, we'd all jump at that. I think there's so many things that we could do with it when it comes to simulating the types of systems, even systems that Bill works with his molecules, for example. Oh, actually, we have our first question. It looks like they came up in the Q&A.
Oh, great. Thanks for. Oh, what does room temperature superconductivity help us with?
Yeah, so we transmit electricity mainly by copper. So copper is like a very good conductor and it's relatively cheap. So room temperature superconductor would be able to conduct electricity though without creating heat. And that's a big issue with normal metals. You can conduct electricity, put it between cities, but you lose a lot of that power that you're transmitting in just heating up the wire, which is useless unless you want to create a heater. So superconductor idea with superconductor is that it could carry that current. It could travel really, really far, and it would not heat up. It would not dissipate because it has zero resistance. That is a key point of the superconductor.
So it save a lot of energy and be very helpful in reducing the amount of carbon dioxide in the atmosphere.
Yep, exactly. And also you can make really good magnets out of it, right? So your MRI machines rely on superconductors actually to operate, and they're very expensive to operate as a result. If you had a room temperature superconductor, you could create MRI machines that aren't as expensive, and you could also create maglev trains that levitate much more cheaply too.
And if you could do superconducting without liquid helium, that would be good because helium is a rare resource, and it leaves the atmosphere. So we've only got so much in the earth, right? So that would be another benefit, many benefits.
Yep. Yeah, liquid helium is used for cooling down the MRI coils.
Great. So that was a great question. And please feel free to ask any question because I know there's a lot of words flying around. I'm trying to do my best to ask some questions, but if you've got anything that pops up, let's do it. Sandy, I wonder if I could turn to you. So the current reality of quantum computers, we're not there yet. Can you talk to me a little bit about, well, what do you think might be possible even with the current computers that aren't perfect, but the systems of qubits that exist that are kind of noisy? Or are there things that we can do now that are interesting?
Well, the first, quantum supremacy experiments were done a little over a year ago now, and that was a completely manufactured problem just to demonstrate that quantum computers could do something that classical computers couldn't. So not a particularly useful problem, just designed to kind of show that difference. The hope is that the next step will be to do something that's useful, and people are mostly focusing on algorithms in chemistry. So given a set of nuclei in 3D space, find the lowest energy wave function of those electrons. And what quantum computers seem, the current generation, they have trouble with computing for very long periods of time. So we use the circuit model basically to sort of talk about, quantum algorithms. And it's the depth of that circuit, the number of different time steps that you need to compute different operations. And they can't go for too long or they start to decohere. So people are trying to devise algorithms that have very short depth of circuits, but you just run them many, many times. And so there's sort of these trial and error algorithms where you plug in a set of parameters, you see what your energy is, and then you kind of repeat this. So they're kind of more of a hybrid classical quantum, because there's a classical side in which you're optimizing your parameters, and then you use your quantum computers to say, okay, with this set of parameters, how good is this, configuration of molecules. So right now, the focus is on these sort of hybrid type algorithms.
Interesting, thanks. So we've got another great question here. What kind of qubits does the IBM quantum computer use? And then there's a follow-up.
I can take the cryptography question. I don't
okay.
know what the hardware is underneath the qubits for the IBM.
So IBM uses superconducting qubits, as does Google. I think they do kind of slightly somewhat similar types. And then, okay, so I mentioned trapping atoms by lasers. So that's not what IBM and Google use. That's a very different technology, but there are various startup companies that use trapped atoms. There's IonQ is one big one that came out of University of Maryland, and there's some other ones that are coming out from Harvard, but those are kind of more recent developments as well.
Great. Yeah, and Sandy, do you want to take the factoring numbers cryptography question?
So cryptography is figuring in very heavily to quantum computation, because one of the first, the star quantum algorithm was developed by Peter Shor to factor large numbers. So if I give you, a 200-digit number, can you find a prime number that evenly divides it? So it seems like an abstract mathematical question, but the crypto system RSA, which basically you use every time you send your credit card over the internet, is based on the hardness of this problem. So if you could factor numbers, then you can break this crypto system, the one that we currently use today most commonly. Now we're a ways away from actually realizing a quantum computer that can actually do this efficiently in terms of the technology, but it has sort of sparked this revolution in cryptography, because first of all, we now need to develop new crypto systems that will be hard for even a quantum computer to break. So that's a big field in and of itself. But then there's also, can we use quantum itself in the crypto system? So there are certain protocols for like quantum key distribution that actually use principles of quantum mechanics to provably sort of securely transmit information. So there are sort of two parallel branches of research that have sort of come out of this.
So
Great.
Sandy, they're working on the next generation of how to protect your passwords, right? Because if the quantum computers can decrypt everything, then we can't use passwords anymore. We won't be able to use.
Yeah, so we need
what would we do without passwords, right?
Or the ability for internet commerce, for example, to sort of transmit your, financial information over the computer. So a lot is riding on the security of this. So, and even if it's 20 years out before we can build quantum computers that can factor numbers, people can go back and decrypt everything that's been transmitted now. So, so that's another
Andy, you're freaking everyone out.
He's on the job though. She'll figure it out for us.
Yeah.
So let me ask, we've got a couple questions here about energy storage,
Right.
which, we know is a very important question as we move into sort of a more electrified energy grid. And the question is, what about quantum engineering and quantum design for new batteries and energy storage? I'll mention something, we have a faculty member in physical sciences, Hulin Sen, who works on next generation batteries. And the goal there is to build lithium batteries without cobalt and have energy storage that's sort of 10 times the capacity per weight that they are right now. He's utilizing interesting kind of machine learning algorithms to do this. But my guess is, so, again, in this era where you have quantum design with a quantum computer, I'm sure that there's people thinking about that. Maybe one of you knows more about that than I do, but that's one thing I could mention.
Well, I would just respond to the questions on that in terms of what materials is. That's one of the reasons I work with these rare earth metals, because they behave like differently from all the other metals that you're familiar with, copper and nickel and cobalt and iron and things like that. And so we're trying to get these special properties of the rare earths to be better for for energy storage. But we really don't know a lot of details about the solids and how they work as well as they do. So these iron neodymium boron magnets, the best ones have a little bit of dysprosium, another rare earth. So it's mainly neodymium, iron, and boron, but you have to have a little bit of dysprosium to get highest performance. So how that works and how that works on a molecular level, we don't know. And that's why chemists like myself need to talk with Javier to try to figure out how you go from the molecular level, which we understand quite well, to this materials level, which we don't understand as well. So this whole quantum science is related to the fact that we really know how to manipulate molecules, single molecules. We're really good at that. And we know how to make macromolecules. So your clothes are made of polymers. We can make polymers, really good plastics and everything, right? But in between, going from molecular to something that's maybe a two-dimensional sheet like Javier's, that's really difficult. And so that's a whole nother area that quantum science is probing, this intermediate size range that we really don't control very well. And I think that's what's going to help us get better energetic materials. So.
Fascinating. Thank you so much, Bill. So the next question is about nuclear fusion. How can quantum science help realize that? Does anyone want to take that? I have a couple things I could throw out there, but I wonder, I'm going to leave it for the panel first.
I mean, I love this question because like this is like the sort of question that like I think normally doesn't come up, but should, you know, in the, you know, say among, you know, people who are doing quantum science research. I think the one thing that I'll just throw out there is that actually it's not what we normally think about, like nuclear physics and how it being quantum mechanical, but it is. And actually, this has become a more recent area of research, is trying to gain quantum control of objects inside of the nucleus of an atom. But it's a very recent thing. So my only comment is that like our ability of quantum control on that scale is very cutting edge and very limited, but it's an area of interesting future research. But I'm curious what James is going to say about that.
You know, I think about what the plasma physicists at UCI, you know, worry about. And I would say starting, you know, first of all, computation and simulations is crucial to what they're trying to do, because these, especially the very large scale fusion experiments, are incredibly expensive. And so you want to understand the setup as well as possible before you try to make it work. And the less trial and error it is, the much more efficient it's going to be. Thomas Edison kept trying different filaments, right? Thousands of filaments until it worked. Well, with fusion, each run costs, $100 million, and so you can't just trial and error it, right? You got to really be a bit more informed about what you're doing. So I think that's one aspect where just better simulation will be helpful. But I think another thing to think about just in terms of materials is containing this fusion, building materials that actually can sustain these strong magnetic fields and get the kind of setup you need could also be a direction that could be incredibly interesting and important. And then finally, another way to think about doing fusion is with beam acceleration. And if you're doing beam acceleration, I could imagine that there are mechanisms where you could apply either quantum computation or some new sort of materials mechanisms to accelerate these particles to really get them going fast enough to get this fusion to happen. So I think it's a bit untapped, like Javier said, but boy, it's fun to think about, and it is a really fun question.
Yeah, those things you mentioned, James, is exactly kind of what I was going to hit on. Yeah.
Great. Well, that's good. That actually makes me feel better. Great. We've got a question. Can quantum computing be used in Monte Carlo simulations, calculations like of physical processes, radiation transport, et cetera? Maybe Sandy, I don't know. You want to?
Yeah, so there actually is, we think of Monte Carlo algorithms as a classical algorithm to sort of optimize certain properties of quantum systems, but there's actually a quantum version of Monte Carlo that looks very intriguing, that can actually store, that's actually kind of simulating this Monte Carlo process on quantum states. So your quantum state is a distribution over different quantum states, and you sort of eventually end up at a distribution that models, something that you're interested in. So yeah, that's actually an exciting area. And we're a ways away from quantum computers that can actually implement that algorithm, but that's certainly something that people have developed and are thinking about for the future. So,
but I think it's fair to say that our classical computers can still do a lot of good for us, and there will be, I think, as I understand it, there'll be some problems that the classical computers are just fine. We don't need the the quantum computers to do those problems. Is that
In fact, better in some cases, because, I mean, we imagine that I/O is going to be a little bit slow with quantum computers. So if you've got a heavy data problem, probably your classical computer is going to be a better fit. So, there will definitely be trade-offs between the two.
Okay, great. I'm glad to hear that, Sandy, because I learned about that from looking at a video on quantum computing, and you've now verified it. So you never know what. So it turns out that Javier and I ran a course this last winter quarter on quantum science for undergraduates to introduce them to quantum science. And as part of that, I asked the students to assemble videos they could find online on YouTube or something on quantum computing. And so they all sent me these videos, and I've been watching them, and I've been learning from these videos. We have them on our Edelman Quantum Institute website. So if anybody wants to see a whole list of like 1 minute on the Schrodinger equation, can you believe that? Or 6 minutes on quantum computing, and they've got great visuals. If you want to look at that, go to the EQI, Edelman Quantum Institute is EQI. If you Google eqi.uci, you'll get to the site, and there's this whole list of videos that teach you about quantum mechanics in various levels of detail, and they're all pretty fast and interesting. Anyway, we had a great time with this course. We had 40 undergraduates that wanted to learn about quantum science. So,
well, I want to take it the next time you offer it, so I hopefully you'll let me
You're
know.
welcome.
I have to say, I'm so excited about these courses. We have this vision with EQI that eventually, we will be educating the next generation of the quantum workforce at some level, right? These big companies like IBM, we talk about building these quantum computers where, well, they're going to need people to run them and participate in all this quantum design that we're talking about. And very proud of the fact that, folks like you, Sandy, you're teaching this course on quantum computation, and Bill and Javier are teaching this course on quantum materials, and we hope to do more of that for our undergrads.
One thing I introduced in the undergraduate class is some programming exercises. So I had taught it to graduate students before. It's purely a theory course in which pencil and paper. But IBM has a wonderful platform for actually programming and simulating quantum circuits. And you can visualize the circuit and see the output. And it really made it more concrete for the students to be able to actually program the algorithms that they were learning about. So there's a lot now in the educational domain that makes this, it makes it much easier to present to undergraduates. So.
I'd like to take your course also, Sandy, but I don't think I have the prerequisites.
I'm sure you'll be fine. We had a lot of physics majors in there, and they were great.
This is wonderful. Oh, we've got a great question here about quantum computers. How do quantum computers create the entanglement between groups of qubits, and what does that tell us about entanglement in general? Javier, you want to jump on that one?
Yeah, sure. So maybe I'll answer the question in reverse. So the funny thing about entanglement in general is that it occurs very easily, actually. So if you just take like two atoms, right, and imagine there's an electron on one atom and not in the other one, and you just bring them close together, the electron can now hop from one atom to the other and back. And just the act of this coupling between these two atoms, it very naturally leads to entanglement between them. So really just coupling two quantum objects together, they just naturally evolve in time and start to become entangled. And so the trick with a quantum computer is, how do you do that controllably? How do you turn on that coupling and turn it off? So because this entanglement is like a dance, okay? It evolves in time, all right, oscillating in and out, and you only want it to evolve for a certain amount of time and then turn it off. That's part of your processing. So quantum computer, as I was mentioning before, you have these qubits which are isolated. You want them to be separated from each other, and then you want to couple them, have them talk, entangle in some amount of time, and then turn it off, and then maybe have them connect to a different pair. So that's the idea.
And from the computational point of view, we know that entanglement is sort of an essential ingredient in a quantum advantage. So if your quantum computer is always in a low entanglement state, then it can be efficiently simulated by a classical computer. So in order for quantum computers to have an advantage, entanglement is an essential ingredient in there. So.
Great, thank you. So now Mark has a question. how close is either academia or industry to a functioning quantum computer for use in the business or research world? How close are we to having something that's useful?
I think the hope is that in the next few years, they'll have quantum computers that can start to solve some of these problems in chemistry that we couldn't otherwise do. So that's, I think the hope is that that is on the next few years horizon. My understanding is that the Google folks and the IBM folks are hoping to do that. There are companies sprouting up all over the place, like QC, where many of my colleagues, have consulting gigs that are actually already designing algorithms for use in the business world. So people are ready for it when it actually happens. But I don't know if Javier or Bill, you have a better idea of that.
Well, I would just say that I think a guy named DiVincenzo at IPM wrote out the needs of a quantum computer in about 2000. Right. So in about the year 2000, we knew what we needed to have. And we've got some operating ones now 20 years later, but the time scale is not as fast as we would like it to be. Maybe.
Yeah, but it took a very long time for development of modern computers, right? From the initial descriptions, right?
Right.
So,
right.
I mean,
so, yeah, we're in like the age of the vacuum tube.
Yeah.
With quantum computing. So, good things are on the horizon, but, these things do take time. I think having the big companies like Google and IBM and Microsoft get in the picture has really accelerated things. So I think Google's breakthrough 53 qubit computer was sort of an exciting surprise to many people. So.
Yeah, I mean, it is a very exciting time to be honest. And so answering on the research side, for sure, already it's interesting. Maybe not yet for simulating full chemistry yet, but I can tell you in the physics side, we're already very excited because people are making, so there's a distinction between like a universal quantum computer and then kind of like a controlled quantum system. So a universal quantum computer is one that will run for you these, Shor's algorithm, for example. You can program different algorithms onto it and it'll do it. There are specialized kind of quantum computers, or what we call quantum simulators, which can already they produce results that are really hard or impossible to simulate classically. And those are interesting for us as physicists because we're like, wow, okay, because we can't simulate this, so we don't know what it's going to say. And these are coming up now with these systems that have 50 to 100 to 200 controlled quantum objects, I would say. They're qubits, but they're not qubits they're not fully connected in a way that can make a full computer, but it already creates results that you cannot simulate and are interesting for simulating materials, for example.
So is it fair to say that these, quantum simulators can simulate a whole class of families that are closely related to what they are, in terms of the materials, or they're still slightly programmable? You can.
Yeah, so I think you could say they map well onto simulations of magnets. So they're spin systems, and especially in the case of these 200 atom simulations, which are trapped by optical tweezers. Those simulations are already kind of producing some pretty mind-blowing results, which is pretty exciting.
Have control at the qubit level, or is it sort of the same sort of term across all of the different pairs there?
So they can, these are atoms that are trapped by optical tweezers, and they can control how close they are and how far away they are from each other, for example. Yeah.
I would just add to the timescale level that I've heard people say that the computer companies cannot get enough educated students fast enough, that they just want to hire everybody. So there's this big effort now, which hasn't happened in 10 years ago, it wasn't that way, but right now there's a tremendous effort to develop this quantum computing. And that's why at UCI, we want to educate the next generation, because there's going to be a tremendous demand. And so we tell our students that if you go in this area, you're likely to have a good opportunity for a job in the future, because there's this tremendous demand.
Yeah, I'm aware of at least 3 courses: the course that you two taught, Sandy's course, and there's another course in the physics department that Steve White has recently put together that I think is sort of in this space. And I can only imagine, I hope that we actually create I know that, Bill, you're working to create a coherent program with Javier and physical sciences to do to create quantum science minors for chemistry and physics, and move that into even the PhD program in this area too. So we're really excited about this direction at UCI, and actually very fortunate that we have folks like Sandy who we can collaborate with, and the computer science on this.
Well, the class was a joy to teach because the students were so excited. I don't know that I've ever taught such an excited group of students before. So they're also keen to have these opportunities too. So
yeah. Well, we've got about a little under 10 minutes left, and I want to encourage everyone to ask questions, but maybe I could throw this back to Bill. Let's think about the future here. Where is all this going to go, and what do you think the future of quantum science is over the next decade or so?
Well, as I said before, I think really we're going to find some things we're not expecting as we go to this very focused target of good qubits, noise-free qubits, and quantum computing. We're going to push the limits of chemistry and physics to get new materials that are going to be good for other purposes. So, yeah, that's all I see in my crystal ball. But that's a lot.
That's good. Yeah, and I like this idea, Javier, that you had talked about, is sort of using the quantum computer to build a better quantum computer ultimately, right? Because it's sort of it's a really positive feedback loop. I don't know if there's anything else you want to add to sort of where you're going in your research and the direction you're excited about.
I mean, that's one major dream and challenge of my area of research, is that we realize that qubits, making a fundamentally new type of qubit. So right now, the way that quantum computers groups are operating, they need to put together thousands of faulty qubits to make one, and have them kind of they basically do what's called error correction to make one good qubit, and then they're going to build their quantum computer off that. So what we're really trying hard on my level, in the condensed matter physics level, on the hardware level, is we're trying to make a fundamentally new type of qubit that will be fault tolerant. So you don't need to have this error correction. Okay, one idea for how to do this is what's known as a Majorana bound state. This is the effort that, for example, Microsoft has been investing a lot of effort into doing, but they've had trouble fully realizing its potential as quickly as we hoped. And so this is a big active area of research in my field, coming up with new materials that can be used as hosts for qubits for quantum computers, but also for sensors as well. This is something my lab is very interested in.
And I just want to jump in and say, one of the other things I'm excited about in the Edelman Quantum Institute is for people like myself, chemists working with people like Javier, to make these new materials, because the physicists usually work with materials they can buy or make fairly straightforwardly. We can design materials, and that intersection, I think, is going to be very powerful in quantum science and in other places also.
Sandy, we've got a couple questions here that are maybe appropriate for you. Another question about quantum entanglement and the potential use for communications and encryption. Maybe elaborate on that a little bit. And then qubits and neural nets, maybe can we use qubits to do some kind of machine learning better than we can do now?
all right, yeah. So there are some protocols that use entanglement to actually, transmit information. They're more focused on efficiency of in terms of, being able to transmit more than security. A lot of the applications of quantum to cryptography are more about securely transmitting a secret key between two parties who want to communicate. So, and that can be done in a completely informationally, theoretically secure way, as opposed to relying on the hardness of some problem. That's actually, and that does use harness quantum entanglement to do that. So there are sort of applications in that direction.
So it's not just breaking everything down. There's also paths forward for cryptography when it comes to
yes, yeah. So there are, and there are also, as we said, the post-quantum cryptographers are working on just classical crypto schemes that are based on a hardness assumption that we think will be hard for quantum computers as well. So, and the other question was on machine learning, I think.
Yeah, neural nets was the word, but yeah.
Yeah, so that's sort of an active area of research, and the jury's still out in terms of how useful we expect quantum computers to be for applications in machine learning. But, I think it's actually going both ways. So we use machine learning applications to understand a little bit more about quantum algorithms, and And it's quite possible that there will be algorithms that will sort of design better neural nets as well. So, but that's just sort of at the very beginning stages of development. We don't know of anything that will sort of provably be better at this point. So,
a couple questions about applications to cosmology, which I'm afraid is probably me. So, that's an interesting question. I don't know if anyone's really thinking about it. One of the things about at least a good part of the very early universe is it's actually incredibly simple. And it's much easier to calculate what's happening, a minute after the Big Bang than it is to calculate what's going on in some of these 2D materials that Javier studies, ironically, because the universe in the very early times is incredibly simple. But even earlier than that, there are time periods where we think the universe may have undergone phase transitions. And those calculations are pretty hairy. And so I could imagine there might be interesting applications for quantum computing in the very, very early universe to sort of figure out what implications might be there. That's all I've got, but I'll keep thinking about it. Maybe I can come up with something better next time.
I mean, I have heard people who come from black hole information theory side that they seem to be feeding back into the quantum computing and my field. They kind of show up.
So I wouldn't. Yeah, it's interesting. My head didn't go there for cosmology, but I guess that's sort of cosmology. Yeah, that's right. I think.
Yeah, so it's not exactly cosmology, but at least
No, you're right. It's spacey. That's right. That's right. Yeah. Well, I think we're wrapping up here. Does anyone? We have one more question, and maybe Bill, you want to take
other
this?
Fields
Yeah.
Are likely to come into the Edelman Quantum Institute? Well, certainly engineering and biology, both. I mean, developing the qubits will involve engineering to make the physical devices that work. So that'll be important. And we already have one person on the biological side, Thorsten Ritz, who talks about quantum mechanics in biology, and for example, in how birds orient and how they know how to migrate, maybe quantum mechanical. So think about that. So lots of opportunities.
It's going to be exciting. Yeah, this is just the beginning. It's going to get better and better. So with that, why don't we close on that? I'd like to thank Bill, Javier, and Sandy again. This has been fascinating. Thank you so much. And thanks to everybody who tuned in today.
And James, I want to thank you also for organizing this, because every time I talk with Sandy and Javier, I learn something new.
Yeah, this is interesting.
I mean, just having these conversations it's been very, very valuable to me to deepen my knowledge of quantum science.
Wonderful. Yeah, we're going to keep doing it. So this is just the beginning. So thanks very much, everybody. Till next time.
All right. Thank you.
Bye-bye.